This is a 3D isometric view of structural steel channels inside a federated LOD 300 model. But in a digital environment, the utility of this geometry is determined by the specific alphanumeric data attached to it. This is because beneath the 3D geometry, a federated model operates as a relational database. When the metadata taxonomy organizing that database fails, the automated processes relying on it break down. Automated quantity takeoffs return inaccurate totals. Clash detection runs generate thousands of false positives. Submittal tracking becomes a manual, fragmented process. Mastering building information modeling requires managing invisible data structures, rather than simply drafting 3D shapes. To solve this data misalignment, the Singapore construction industry adopted the CP83 standard for CAD and BIM file organization. This standard provides a strict, machine-readable alphanumeric taxonomy, working across siloed architecture, engineering, and construction disciplines. Without it, founds rely on ad hoc internal layer naming conventions. Custom conventions fail during multidisciplinary project delivery because different software systems cannot parse bespoke logic. To understand how the CP83 standard forces interoperability, we have to construct an AEC metadata string from first principles. Every string begins with the most critical parameter in digital delivery, the discipline code, which anchors all subsequent data. Look at this empty framework of a standardized data string container, ready to be populated block by block. The very first field is the originator, or discipline anchor. This establishes who owns the data and holds legal liability for the element. The standard uses specific two-letter codes to identify primary design roles. For structural and architectural design, we use AR for architect and ST for structural engineer. Engineering and site roles use C for civil, ME for mechanical, EL for electrical, LS for land surveyor, and LA for landscape architect. Execution phase roles use CN for contractor and ES for equipment supplier. If a sub-author designation is not required, an authorized variation allows a single character like A, C, E, M, or S, followed by a hyphen. By forcing this prefix, the system instantly ring-fences legal responsibility for every model element before a single geometry is drawn. We can apply these codes to a specific CAD layer name according to CP83-1 rules. Here is the exact target string we will build for an electrical circuit: E-LELCABL R-T. Starting with the originator field, the E- prefix dictates that the electrical engineer owns this layer. Moving to the element field, the standard strictly requires 8 characters, subdivided equally into main and subcategories. The main element is ELEC, designating the broad system of electrical power. The sub-element cable narrows the classification specifically to cable trays. The trailing fields indicate presentation and status. R- denotes a single-line diagram. The final T designates this element as temporary work. This 16-character string eliminates the need for descriptive paragraphs, turning an arbitrary line into a machine-readable, auditable asset. Notice the specific use of hyphens in that E-elec-cable R-T string. In CP83, the hyphen is not a casual spacer. It is a functional command meaning no further subdivision. Database queries parse these strings by exact character position, counting from left to right and locking into fixed column widths. If a user omits the hyphen, the character count collapses. The system misreads presentation data as element data because the blocks shift into the wrong columns. Formatting characters act as structural load-bearing elements. Breaking the character limit breaks the database. This logic scales from the micro level of layer naming up to the macro level of managing files in a common data environment. This is the CP83-3 file naming standard applied to a complex real-world string. The project identification field, SWP, immediately associates the file with the Southwood Point project. The author field, KA, identifies the specific individual or firm originating the file. Next is the recurring discipline code, AR, confirming architectural ownership. The zone block, A2, isolates the file to a specific physical location or phase on the site. The type of work block, SP, defines the file content as a site plan. Notice how underscores fill the unused view plane characters here, maintaining the strict spatial formatting. The version field, C followed by underscores, clearly marks this as the third revision, critical for document control. The optional user-defined field at the end, XYZ, allows for safe in-house operational codes without breaking the universal standard. This file name operates as a perfectly sealed ledger, embedding location, ownership, and time directly into the CDE architecture. The strict alphanumeric rules of the file name must carry over into the abbreviations used inside the model itself. This diagram shows mandatory standardized abbreviations for architectural datum points, such as FFL for finished floor level and SFL for structural floor level. The same applies to mechanical and plumbing systems, using terms like RWDP for rainwater downpipe and CWS for cold water supply. Federated models rely on these exact abbreviations to correctly align physical systems in virtual space. If an architect types f.floor and a structural engineer types fin_floor, the software treats them as two completely different elevations. Standardizing this micro-language of abbreviations prevents false clashes and alignment failures on site. Zooming out to a completed federated project, we see tens of thousands of these standard strings interacting simultaneously. A BIM manager can execute an automated query to instantly isolate only the mechanical components. The BIM execution plan utilizes these specific discipline codes to rigorously enforce limits of reliance and limit legal exposure between parties. This standardized environment allows software to automate tedious data extraction processes without human intervention. The depth of a digital model is only accessible when the data within it follows a predictable structure. By treating AEC naming conventions with the same rigor as software code, professionals ensure that model data remains stable and usable across the entire project lifecycle.